Okay. I could pull up on the forevers, but I think it's already in your notes and it's right down here. So, definition of continuous. The part you need to have memorized is in blue, but then this black summary at the bottom is really important too. I'm going to keep it up there, so I'm going to keep referring to the definition today, especially when it says discuss continuity. When it says discuss continuity in homework or in examples, this is what we're trying to think about what technically needs to be true for a function to be continuous. Yeah? This one is talking about the point existing. At x equals c is there a point. This one's talking about the approach. Are both approaches agreeing? Not infinity, not agreeing to infinity, but agreeing to a constant. And the limit exists. And then does the approach equal the at? Are they the same thing? So over here, if I was to give you this graph, for instance, I think that's a bad marker. Okay, if I was to give you this graph, for instance. Question, is condition number 1 true? Yes or no? Yeah, because at c, is there a function value? Yeah, the at is there. Is condition number 2 true? Why not? Good, they're approaching the exact same height. So the limit exists. The at is there, the approach is there, but where would this type of function fail? Yeah, the third one, right? Because the at and the approach are not the same. And do you guys know what type of function this is? Is this like a polynomial? Is this a rational? Is this a radical? It would be rational. It could be irrational because can't rationals have things like, I don't know, we could do x squared minus c all over x minus c. Like you could have like a 0 over 0 with this guy. So you could have a whole, but the only way it gets filled in is if you have a piecewise function. Because this would be like, hey, everywhere except for c is this function that has a line with a hole in it. But then it's filled in the actual value at c with something. Now, I don't know, something high. We'll get it like 20. There you go. It's filled in the hole with something. There, it's a little bit too intense. So the weird thing is this graph doesn't look that weird because you guys have been seeing a lot of weird graphs. But the equation would look super weird. It's like, what's going on? But basically, it's a line with a hole in it. That's what this guy is. A removable discontinuity is 0 over 0 at c, and then it's filled the hole in somewhere else. So anyway, you're going to be seeing some weird stuff in homework, some weird graphs, some weird equations, and you need to know what to do with it. And it all comes back to the definition of continuous. Now, we talked about a few different dudes on Thursday. Guys that are going to be continuous everywhere, no problems whatsoever, unless they get put together in a piecewise function. You can add them, you can subtract them, you can multiply them by a number, you can divide them. Just watch out for those zeros. So let's check out these guys and let's talk about them, discussing the continuity, because, oh no. Hi webcam, you were so helpful this morning. Hold on, let's try again. Because in your homework, page 96, I don't remember exactly what the problems are, but let's talk about it real fast. First section of homework, what is it having you do? Can you guys see it? Use the graph to determine the limit and discuss the continuity of the function. Out of these 4 that you guys can see, which ones are continuous? 2 is continuous. That's good. What else is continuous? 1. What else is continuous? Nope. Why not? Where does number 3 fail? The third rule. Do you see it like the one on the board? The point exists. He's right there. The approach agrees. Yay! But then they're not the same. So this one fails the definition of continuous on the third rule, or the third condition that must be met. This is the exact same type of failure, right? If you were to discuss it. But guys, so far, 1 through 4, don't all of their limits exist? Right? Because coming in, the approach is good. Coming in, the approach is good. Coming in, the approach agrees. Coming in, the approach agrees. Only these 2, even though the limit exists, the function is discontinuous because of that number 3 failure. But do the limits exist in 5 or in 6? No. So then it actually fails before 0.3, right? Doesn't it fail in number 2 for the definition? Now, what happens down here in number 7 through 28, I think? How do the directions change? Find a limit. Oh, does it even say continuous? Okay, so hold on. Some of you guys might get confused in this section just because all of a sudden we're talking about continuity, definition of continuous, and this one just says, hey, just do the limit. So in number 7, guys, what do you notice about this limit? Why is it a little bit weird? Yeah, it's 8, but it's only 8 from above, right? Okay, well, that's fine. We've seen things like this. So let's plug it in, and when we plug it in, it's number over 0. Wait. It's not number over 0. What is it? So, but wait, I'm coming from above. Am I done? Is that it? Yeah. So when you're coming from above or below, it doesn't make a difference if the plugging in works. I mean, you have to be careful of piecewise functions. Kind of like because of the graphs up above. Because remember, the above or below are different pieces, like whether you're looking in this piece or whether you're looking in that piece. Like with piecewises, we have to be careful. But with normal functions, the above and below agree. Hey, I'm good. I'm golden. That was an easy problem. It was just a plug and chug. Now, what if we were doing something like, oh, I don't know, number 10, and we plug in from above? Okay, so 0 over 0. Well, wait a minute. From above, now what do I do? No. Wrong question. Yeah, 0 over 0, what do we always do? Okay, so try to do it. So don't stress about the above or below. If you have something to do, just go for it. Now this one's a little weird because we end up with x plus 4, x minus 4. Do you guys see that I would want to factor out a negative to make it look all nice and pretty and match? Right? But if I factor out that negative, I know I'm running out of room. The limit's written there. Blah, blah, blah. Okay, we can reduce. And then wouldn't we just plug and chug? Okay, so the above or the below doesn't make a difference if I'm just plugging in and getting an answer, or if it's 0 over 0, keep going. I actually do that work. When does above or below make a difference? Can you guys look at number 13 with me real quick? What's different about number 13? Absolute value. It's coming towards 0 from below. It's 0 over 0, keep going, but how do you keep going? Yeah, you would have to think about this as a piecewise function. So now you would have the negative x's needing to flip, the positive x's getting to stay the same. And so, wait a minute, what's negative x over x reduced to be? What does x over x reduce to be? 1. Okay, so if that's negative 1, and if that's 1, and I'm coming from below, what's the answer to this limit problem, guys? No, I'm coming towards 0. Why negative 1? Yeah, it's the below piece, so we would look at the below piece. So now it was important. The below was important. The above would have been a totally different answer, and then the limit as x approaches 0 would have been d and e because they didn't agree. So in some of these guys, it is going to be important to watch out for that sign, to watch out for that above or below, but some of them are good old-fashioned just limit problems that you're solving without stressing out. Now we do have something weird down here that has to do with the definition of derivative, which is a little bit weird. Then we have these piecewise functions, but we kind of just did a piecewise function about how the above or below just tells us which piece to choose, etc., etc. Anyway, that's the second section of homework. Now, I do want to warn you of something real fast. Who's this little double bracket dude? Hold on, he's coming. Oh, nope, no, he's not coming. He's too high. Who's this guy?
Oh.
Who are these guys? Remember in our basic graphs? The greatest integer function, the steppity step step, like a parking garage?
Oh.
Yeah, it's that one. These guys can be like twisted, distorted, can be stretched, can be translated. Let me show you an example real quick down below. They actually have some graphs in the next section. Do you see how this is a step function, but he's stepping real weird? Right? Like he's a jump function, but in a weird way. It's like little baby pieces of lines. So These can be kind of weird, they can be kind of off, but the long story short is they are going to be doing that weird steppy thing, that weird jumpy thing, right? Just say and then I don't think I gave you guys tons of those. Nice thing is I've never seen one of those on an AP exam. I'm not saying it's never been there, just I've never heard of one being on an AP exam. So we're going to see it just because it's a pre-cal thing. It's a pre-cal thing, but you shouldn't have to stress about it a lot. But sorry, this is what I was trying to get you up to, was number 29. So far, all you've had to think about is, look at a graph. Is it continuous? Are the limits existing? Look at functions. Are the limits existing? And now all of a sudden, directions change a lot. What do you guys see is going on in 29 through 32? Discuss the continuity, but what are you still given? Nice. But what's going on down here? In 33 to 36, discuss the continuity, no graphs. And then numbers 37 to 62. This is where I said you should be able to get up to. Once again, talking about, discontinuities. Removable, non-removable, where it's not continuous. Do you think these might help a little bit in that? I think so. So let's do some practice problems. And I'm going to try to explain, as we do these practice problems, how you can discuss continuity. And not just discuss continuity, but like that huge old massive section of homework. Where are the discontinuities? Are they removable? Okay? So I'm kind of helping you with the discuss continuity section, and I'm helping you with, okay, so if it's not continuous, where is it discontinuous, and are they, might be more than one, removable in that. So, letter A, what do you guys think? Is it continuous everywhere, or does it have a problem?
Zero.
Yeah, it totally has a problem. So this one, letter A, has a discontinuity at x equals 0, but, hold on, wait a minute. Is it removable or non-removable?
Non-removable.
Why?
It's like this.
Okay, I'm hearing a couple things. I'm hearing it like this, and I'm not sure what that means. I'm hearing vertical asymptote, and I'm also looking and seeing what happens when we plug in 0. It's undefined, but what kind of undefined? A number over 0, a number over 0, infinite form, right? Vertical asymptote. So therefore, yes, all of those point to it being a non-removable discontinuity, right? And we could say, since the limit as x goes to 0 of 1 over x is, what is the limit? Not 0. What's the number over 0 point us to again? Isn't this a basic graph too that we could actually kind of visualize it or think about that? What's the limit as I go to 0?
Negative.
From one side.
From the other
From the other side.
infinity.
So what about going to 0? Does not exist. And isn't that enough? Condition number 2 fails. Isn't that enough to say, okay, forget it, discontinuous? So we've discussed the discontinuity. We've discussed the continuity by being like, hey, it's good everywhere except for 0 because the limit doesn't exist at 0. By the way, that means it's not removable. So kind of did all the above. How about letter B though? What's going on there?
It can be made to an x plus 1 thing, but we can't factor it.
Okay, so Joe's saying that we can factor the top to be x plus 1 times x minus 1. Is there still a discontinuity? Yeah. So we still have a discontinuity at
1.
X equals 1, but why am I going to put removable? Joe's going further and saying, okay, if we have the x minus 1s, we cancel out. This is x plus 1. It's x plus 1 with a whole. What's the limit as x goes to 1 of x squared minus 1 all over x minus 1? 0 over 0, so keep going, right? So the limit as x goes to 1 of x plus 1 times... I know. Okay. There we go. It was coming. It wasn't your fault. It was the computer. What's the limit?
2.
What does that mean?
They agree on that point.
The limit exists. The limit is fine. What doesn't exist?
The point. The point doesn't exist. Function.
The function doesn't exist. Yeah, you could actually say f of c doesn't exist, but I'm saying f of 1 because that's where I'm talking about. Now, technically, in letter A, wait a minute, didn't f of 0 also not exist? Does it work to plug in 0 to letter A, guys?
No.
So this one actually failed number 1 and 2, right? The point wasn't there because there's a vertical asymptote and the limit didn't exist. It was infinite and not agreeing. So technically, this one failed condition 1 and 2. This one only failed condition 1.
Removable discontinuity.
For letter C?
For B.
Oh, for letter B. Yeah, removable discontinuity.
Oh.
Okay, so letter C. Ooh.
Piecewise?
Wait a minute. Hold on. You guys just took some notes on this, didn't you?
It's like the,
Isn't x plus 1, isn't that a line?
yeah.
And isn't line technically underneath the whole polynomial category? And polynomials are continuous everywhere. And then the next one is e to the x, and he's an exponential. Exponentials are continuous everywhere.
When they join.
So where's the problem?
It's a piecewise function.
Yeah. And what's true about piecewise functions? Can't they sometimes come together and sometimes not?
Yes.
Right? So what do we have to do to double check? Because he's fine.
0. 0 plus 1 is 1. That's good. But negative 1. Yeah.
That's there's no negative. Okay, so we have to check. And the way to check, and if you were listening to Joe, he was like 0 plus 1. Why was he doing 0 plus 1? What was he checking? Technically, the limit from below. Because isn't that less than or equal to 0? And the limit from below my function, I'm plugging into x plus 1. The limit from above, I'm plugging into e to the x. So what happens if we plug in 0 to the below piece?
1.
What happens if we plug in 0 to the above piece?
1.
This is one of those really weird piecewise functions where
They join together.
fit. Yeah. And if they join together,
There's no discontinuity.
there's no discontinuity. If you guys want to see it visually, you could go ahead and do x plus 1.
So,
And then e to the x would be a
like,
swoop, there it is. And then there's the line. So the line stops, and then the e to the x starts at 0. So even though it's weird, and there's going to be like a weird little cuspy thing is what we call this little sharp turn, technically the limit exists because they join up. And hey, wait a minute, doesn't the point exist also? Because doesn't this say we're equal to 0? So f of 0 is 0 plus 1.
Yes.
So f of 0 exists, the limit as x approaches 0 exists, and they're the exact same thing.
Continuity.
So this guy is continuous for all real numbers. He has no discontinuities. He's continuous for all real numbers, but we had to check at 0. The line, fine. Everywhere except for maybe where they join. E to the x, fine, except everywhere. Well, except for where they meet, we have to double check. That was tricky. How about letter D?
B.
D, as in delta. Y equals sine of x.
I think it's continuous.
Ah, we're hearing multiple continuouses. Wait a minute, didn't you guys just write something down about sine?
Wait.
What was under the common functions that are continuous for all real numbers? Sine x or cosine x. He's continuous for all. But guys, think about it. Doesn't he just keep on going?
Yeah, just
He doesn't have any vertical asymptotes. He doesn't have any holes. He just keeps going.
that's whole other mechanical.
Yeah. So continuous. But some of you, to be honest, would have been kind of stuck on that one for a while, being like,
That's like Boyle's analysis.
Okay. So what am I doing when I'm discussing the continuity of each function? What am I thinking through? Can anybody just kind of, I mean, I know what I'm
Do
doing.
they
Do you know?
abruptly end?
Give me one thing, Joe. What?
Do they actually abruptly end at some point in the function, or they just keep going? That's what we're talking about, and we're talking about.
Not abruptly end.
Like,
Because none of these abruptly end. All of them go on forever left and forever right.
they do not contact.
Okay, so he's thinking specifically of piecewise functions. Do pieces connect or do they not connect, right?
Depends.
But the only one that we had to worry about that was this one, right?
Yeah.
This was the one that had separate pieces. Do they connect or are they broken?
They do.
These ones do, so it was continuous for all real numbers. However, what if they didn't connect? Where would have been the problem? At 0. Because the limits wouldn't have existed. So it would have failed condition 2. So maybe we're looking at pieces and saying, do they connect? But what about these guys? What were we looking at?
Bottom.
Domain problems, because fractions have domain problems like the denominator. So we were like, oh, there's a problem, but we didn't just need to say there was a problem. We had to say what type of problem. And how do we know the difference between non-removable or removable?
Can we fill the hole with 1 point and make the function?
But to think of that, don't we have to think about whether it's 0 over 0 or number over 0?
Yes.
Think about whether we can factor and reduce or whether we can't, right? And then we were able to keep on going with limits, because if it's a vertical asymptote, the limit will be infinity or DNE, which, that's not good. Condition 2 fails. If it's a hole, the limit will exist, but the point won't exist. That it fails too. Okay, so that's discussing the continuity of each function. This is the same one that we just did. Hold on, that's kind of boring. Let me get a new example. I do want us to take notes on this, but that's the same example. Hold on, let's forget him. This is brought up the slight problem that when dealing with continuity and limits, piecewise functions appear, and we don't always like them. So let's do a couple of different examples. One of them, what if I was to give you f of x is equal to, and then another one, let me give you g of x. Let's do something simple like x plus 2 for x less than or equal to -1. And let's do, that didn't help. Let's do the cubed root of x. For g of x, let's do what if we were supposed to think about and discuss the continuity of these two guys? So two different piecewise functions. Two different piecewise functions. Or piecewise questions, piecewise functions, and piecewise functions. Alright. Let's start with f. We're a little bit more used to him. For f of x, could we identify f of, well, hold on, wait a minute. Does this guy have any problems in and amongst himself? X plus 2. Could he be discontinuous by himself anyway? Nah, he's fine. How about the cubed root of x? He's fine too. He's not a square root. He's a cubed root. I can have positives, I can have negatives, I can have zeros. Okay, so top guy, no problems. Bottom guy, no problems. The one thing we have to think about is, do they connect, right? So, definition of continuous. Does f of -1 exist? Yes or no? Yes. How could I find him? Which piece of? Because or equal to, right? So I could plug in -1 plus 2 is equal to 1. Condition number 1 is met. Check. Okay, what's condition number 2? Okay, so I have to do the limit. Wait a minute, but I have 2 different sides, don't I? Okay, so I have to take the limit as x goes to -1 from below. I take the limit as x goes to -1 from above. And I have to compare. So what am I plugging into if I'm coming from below -1? Okay. I think I have to plug into this one again, right? Because it's the less than. So it would be -1 plus 2, which would be 1. And then coming from above, where am I plugging it into? Yeah, the other one. So it would be the cubed root of -1, which is, uh-oh. Is that good or bad? So what can I say about condition number 2? Because the limit, they both have to agree, don't they?
Yeah.
So is the function continuous?
It's not.
Where is it discontinuous?
Saying it.
The second one fails, and it's discontinuous at
It feels number 1, 2.
x equals -1. So this one might be a little bit more confusing as to whether it is removable or non-removable, because it's a piecewise function.
It's not.
It's not a point discontinuity, because it's not just one point that's off, it's like an entire function is off, right? The whole function would need to be shifted. So we can't call it a point discontinuity. It would be technically like a break.
Irremovable.
And so as a result, yeah, we'd have to say non-removable. There are other ways of describing it. Let's just say he's not a hole that can be filled. Now how about g of x though? And the nice thing is the definition, as soon as one fails, we just say, okay, fine, discontinuity. What about g of x? Does, well, wait a minute, hold on. He has a denominator, right? Uh-oh, x can't equal 2. Oh, we know that. Oh. Well, then is he fine everywhere but here? Uh-huh. So therefore, okay, well, let's not worry about him, and he doesn't have any problems. So, all right, f of 2. Let's just check the separator. He's fine everywhere but the separator, so let's check the separator. Does f of 2 exist? Oh, not f, I'm sorry. What's his name?
G of 2.
Yeah, but does he exist? Yeah, because look, isn't it 3? Oh, that's easy. But how about condition 2? What's the limit below? Wait. Do I have a piece for below and a piece for above?
No, you just have 1. It's the same
So,
function.
can't I just do one limit?
Yes.
Because can't I just look at the piece that's below and above? Uh-oh, I can't write the number 4 though, that's an awkward thing. 4. What happens when we try to plug in? I don't even care about the at, do I?
A squared minus b squared.
I just care about the approach, so I really just have to look at that too. Joe's seeing is the difference of squares. Do you guys see him? He's 2 minus x, 2 plus x. So then that guy's going to reduce. Ooh, do you guys see though that it's going to actually end up being a negative one?
You're going to have to add negative.
So you have to pull out a negative, and then you're going to have an x plus 2, and your limit's going to be, does the limit exist?
Uh-huh. In the bottom. Isn't it should be
Oh,
in the
thanks,
bottom?
Joe. I'm too used to me making different examples. Awkward. It's going to be
2 plus x. Wait, is it x plus 2 or 2 plus
2 plus x, x plus 2. I would have pulled the negative out, so I would have had an x plus 2, x minus 2. So then it'd be -4, right? The limit? Boop, boop. But still, the limit exists. Oh, so condition 1 is good.
That
Condition
point
2 is
like,
good.
It's not on the function.
But what's the problem?
The point is somewhere out of the function.
Condition 3, they don't match. So g of 2 does not equal the limit as x approaches to g of x. But why is this guy a removable
Because you can
discontinuity?
just take off the pointer and everything's good.
Well, it's not quite that simple just because, Joe, if we take away this, he still has a problem.
There's a hole in it.
But you could fill the hole and then it would be okay. So if we redefined this one, if we redefined it, it would be alright. All we have to do is fix a point. This one we'd have to make the two functions match a vertical asymptote. Well, we have major issues there. But do you see the difference, guys, in how I tested these two? This one had a below and above, and so I had to do the limit separately. This one, though, all I had to do was really the limit of that top piece because he was both the below and the above. Just something funny to keep in mind. What? Hold on. What is this thing? It's not saying discuss it. It's not saying find a distance
Find
to
the
do it.
value of A so that it's a continuous.
So the answer to this is A. I'm making it continuous?
Yeah, plug in value.
How can I make it continuous?
Make the same value the same thing.
Make them connect, right?
Yeah.
If I can make them connect, then I can make it continuous. So does f of negative 1 exist? Yeah, it would be a times negative 1 squared plus 1, which is a plus 1?
Yeah.
Okay, well, I don't know what that is. I don't know what a is. All right, keep going. So the limit, as x approaches, do I need to do just one limit, or do I need to do two?
You need to do two.
Okay, because I have a below and I have an above, right? Okay. So the below, wouldn't I be plugging into 4 minus x squared? 4 minus negative 1 squared? What would that be?
4 minus 1 is 3.
Yep, that's 3. Okay, and then this one, if I come from above, where am I? Wait, we just did that, didn't we?
Yeah, that's it.
We got it was a plus 1.
0.
What needs, no, not 0. What needs to happen for this to work?
It's got to equal 3, so A is
Don't I
3.
need the two one-sided limits to agree?
Oh, that makes sense. So A is 2. That's it.
If my one-sided limits agree. Guess what? This is where homework goes after number 62. And beyond, you guys got a whole example to let you go farther than 62, but go at least to number 62. Sound good?
Yes.
You have a little bit of grade 0 for your morning. Oh, I forgot. Bye. Take it. Have fun with limits and continuity. Not that you want to like.
What is the? Put the
got
correction. This is the worst.
Oh.
Wait.
Look up there. There's a folder that says period 6. But
Period
there are
5.
two different findings. There are
Period
two
6.
different.
Oh.
Everybody got confused. Okay.
None of them put it in that
None of
folder.
them put it
That's
period
the thing.
6. They saw it and they thought they knew what was going on.
Yeah. I was like,
Yeah.
because.
It looks like period 6 and then period 1 is covered up.
Yeah.